going to end up being a homomorphism, but you're going to go from GL to Q. So it's going to be the matrix.
GL to Q.
Yep.
Okay.
And then you're going to go to Q minus 0. So it's going to be like all Q about 0.
Wait. We have GL of 2 of Q.
Yeah.
It is.
It's going to go to.
It is just a moment. It's all matrices of size 2 by 2
Yeah.
with rational coefficients
Yeah.
with non-zero determinant.
Yeah.
Then there was a mapping to Q.
Minus 0.
To Q minus 0.
Yes.
Right.
Yes, you don't have to.
And this mapping, we know what it is. I suspect
Yeah.
that it is determinant.
Yeah.
Okay. So what's the question?
It says prove that it's onto but not 1-to-1.
Okay. So let's discuss what it means. Onto means that for every non-zero number, there is a matrix of size 2 by 2 with this determinant. So the easiest way to address it is just to show such a matrix. So can you help me here?
Yeah.
Suppose I have number D, which is rational, but not zero. That's our modern notation, right?
Yep.
Can you present a 2 by 2 matrix with determinant exactly D?
It's 8, like,
2 by 2 matrix.
oh,
What? Yeah.
oh, it's AD minus.
There is a very simple matrix with this determinant.
Minus that.
Huh?
Did you do the identity matrix?
Identity matrix not quite good because identity matrix will have determinant 1. And I want
Is it going to
determinant
be D?
So identity
D0,
matrix is
0,
a,
D? Yeah.
that's what you're suggesting?
Yeah.
Okay. That's okay. Yeah,
Oh,
that's
yeah,
certainly,
one, sorry.
yeah, that's certainly okay.
Yeah.
Yeah, okay. Now the claim is, so we proved first part of this claim, right, that it is on. Why it is not 1-to-1?
Because it could go to.
Because there is a lot of matrices with this.
With this
determinant.
determinant, right?
Say, the stupidest other example would be, say, D001. But here you have some problem. If D is 1, it's the same matrix. Okay. So,
You can put any number.
how about doing this? Then it's for sure will be different.
Or you could even take one of those diagonal zero elements and make it anything else.
Or,
One of them.
okay, well, not one of them, both of them. Or you can take, that's maybe your suggestion, not quite refined. Now, how about this matrix? No matter what is T, just any non-zero number. I'll write it like this.
But what would have been wrong with taking, like, let's say our first matrix, take one of the zeros and make it like 5.
Here?
No, zeros, one of the zeros.
Oh, thank you. Yeah, sure. You can put any n here.
And you could do
So
the
you
same
have
thing.
a lot of matrices with determinant equal to. Okay. Now, how to understand it? It should be about the same amount as matrices with determinant 1. Because what would be kernel of this mapping? Kernel of this, it's a homomorphism. So I write it this way, then it's a group homomorphism. And what is the kernel? All matrices with determinant 1. Do you know how many matrices there is with determinant 1? Well, it is matrices A, B, C, D, which satisfy just one relation. How many parameters I have?
4.
And I have one relation. So how many degrees of freedom I have? What do you think? How large is this thing? How many? You understand what I'm talking about? Degrees of freedom? Okay.
24.
It is like a curved something in 4-dimensional space, right? You understand? We have 4 variables, right? And then this will give you something there, okay? How many dimensions this something is? What do you think? You understand where 4-dimensional space comes from? Because I have these four numbers, A, B, C, D.
Right?
Right? They determine four-dimensional space if I don't have any relations between them. And now I have just one relation. So it restricts my set of. So instead of, if I don't have any relations, I have just four-dimensional space. But if I have one relation, what kind of a dimension do you think this thing will be?
3.
Of course, 3, yeah. One relation, 1 degree of freedom gone. So, a thing like this is called threefold. Official name to it, threefold. Something which is three-dimensional. And I should report to you that research of threefolds is not finished. We still have some questions about threefolds, which we don't know how to
I'm sure
answer.
it wasn't fun.
Don't know how to answer. So you have a lot. And of course, look, now take any matrix with determinant D, say this one, or this one, or whatever. Take one matrix with determinant D, say this one, and multiply it by any matrix with determinant 1. Then this product has determinant D, right? Because you remember, determinant of product is product of determinant. And that's description of all matrices with determinant D. Because if you have two matrices with determinant D, then their ratio, no matter left ratio, right ratio, will have determinant 1, right? If I have matrix alpha and matrix beta such that determinant of alpha is equal to determinant of D, then determinant of alpha inverse beta is equal to 1. The same formula. Okay? So it's by far not 1-to-1. But again, you remember we discussed this 1-to-1 thing. What regulates 1-to-1 when you have a homomorphism? Kernel. Thing is 1-to-1 if kernel consists only of one element. So that would be an appropriate thing to think about in this context. What is the kernel? All matrices with determinant 1. Is it just one matrix? No. Certainly not just identity. That's nice. Okay. Next question. Next question.
When you say kernel consists of only one element, it doesn't have to be the identity element, does it?
Of course it should be identity element because kernel is elements which are mapped into identity. And whenever you have a homomorphism in group context, in ring context, whatever, in linear algebra context, neutral element always go to neutral element.
Huh.
We discussed with you, right, that under homomorphism, let's talk about groups. If you have homomorphism one group to another, then identity always go to identity. Correct? Or it's confusing again. Do you want me to explain again why identity under homomorphism go to identity?
I guess I was
No skin
thinking,
from my nose.
I was thinking of an example which is more like in a ring.
In a ring, then you have to talk about zeros. It's different.
You don't just have one at any element in the ring, right?
Okay, if you have a homomorphism of a ring,
Yeah.
then 0 must go to 0.
Okay.
Now, with definition from your book, 1 goes to 1. But that's just artifact of your book. In different book, it's not necessarily the case. Okay? Because in different book, ring does not necessarily contain identity, multiplicative identity. And of course then you don't have restriction with under homomorphism. Non-existing identity goes to non-existing identity. Okay, so in different book, rings with identity will be called rings with identity. So axiomatic of a ring would not contain requirement for multiplicative identity to be there. In your book, it is. Right? When you look at axioms in your book. I think, by the way, in first edition, I think is it a third edition? Yes. I think in the first edition they didn't require existence of identity in the ring to be true. So they changed their mind. Anything else to ask? No? Come on.
What's a relator?
relator. So, is it used, by the way, this term in your book?
You used it in
I
lecture.
use it, yeah. So, in this presentation of S3, which I just wrote, and there is AB, A cubed is B squared is identity, BA is A squared B. These two expressions, these two symbols are called generators. And this actually, I have three here, not two, you understand? 1, 2, 3. These are relators. It's not universal, but that's relation which are here. So as I said, disadvantage of giving a group with help of generators and relators is that sometimes by what you see, you cannot make good judgment about your group. You cannot say whether it's just identity element. Because you see, if you have any bunch of generators and relators, one group certainly will satisfy all of them. If we take, just in this example, just think that A is identity and B is identity, then all of these relations are satisfied, right? So all these relators are also correct. But it's not really interesting. So in some cases, you cannot algorithmically resolve this question. But this is kind of a desperate question about relators. Because you don't have anything to ask. You're ready for a test? No? Okay.
Page 141, 14.
141. And number is 14. 141. 14. Prove that any cyclic group with more than two elements has at least two different generators. Okay. So, if we have a cyclic group, this cyclic group is generated by one element, right? So we can call this element G. Right? Now, what are generators of this group? What are generators of this group?
Powers of G.
No, that's elements of this group. Which of these elements are generators?
G.
G generates everything. Now, what is called generator? Another element which also generates everything. So what is the claim? That should begin. Any with more than two elements has at least two different generators. Okay. Do you have some nice example of a cyclic group in your head? What would pop up? A cyclic group. Example.
Z6.
Z6. Okay. How about Z6? So 1 generates Z6. What else generates Z6?
Oh.
5 generates Z6. So any number which is relatively prime to 6. Okay, with this 5, it's hard for you to see the pattern. Can you redenote 5? It will stay 5, but you will denote it differently.
Minus 1.
Exactly. So how about 1 and minus 1? And how about in this language, if this is G, what is minus 1? What corresponds to minus 1?
G to the negative 1.
Exactly. Okay. Cool. So clearly, this generates the same, right? Okay? So now our question. Why they're talking about this, at least 2, 3 elements or whatever, more than 2 elements? Why? Apparently because they want G to be not equal to G inverse. And what will happen? What we have to exclude them? What will happen if G is equal to G inverse? It's the same as to say that G squared is identity. Oh, that's exactly cyclic group with 2 elements. That's why we exclude it. And certainly in cyclic group with 2 elements, you have just one generator, right? Just 2 elements. 0 and 1, or if you want multiplicative notation, say 1 and negative 1. You don't have just room for another. But if it's larger, then these two guys are different, and so you have two generators in his board. Okay, next question. Next question. By the way, in Z, that's a good example also of cycling, right? You have just one and negative one, and that's it.
Exponent of a group.
Exponent of a group. Okay,
Is it
that's a
these
notion
some
which we didn't. I don't believe that we really used it in our course. I think in 543 it's used for something or other. But exponent for us is just definition. It's the smallest number such that any element of your group raised to this power give you identity.
Least common multiple of the orders of the elements, right?
Least common multiple of all orders of your group. So it can be infinite. You understand, yeah? Or not defined, whatever. Because nobody told us that all orders are finite. But even if all orders are finite, it still can be infinite, right? Because suppose, of course, it should be infinite group. If group is finite, then certainly it has exponent. How do we know it? Because any element in degree which is equal to the size of the group is identity. It's Lagrange theorem. So exponent is not larger than this number. It can be smaller, certainly. But if group is infinite, it's still possible that every element has finite order. Say, how about such an example? Take Z2 cross Z3 cross Z4 cross Z5 cross blah blah blah. You understand what I'm doing? I'm taking this direct product of infinitely many groups. Of course, every particular element will be of finite order. With right understanding, what is this direct product? Okay. So there are these two different notations, direct product, direct sum. So what I'm thinking about is elements such that first enter in Z2, second in Z3, and so on. But for every expression like this, starting with some point, every entry is 0. You don't know at which point, but of course, if you take element 1, 1, 1, its order will be infinite. But if you have this additional condition, from some point it's all zeros, and every element will be finite, but nevertheless, exponent will be infinite. Not very interesting, anyway. You're asking desperate questions today. Questions for sake of questions. Because you don't need to know what is relator, what is exponent, in order to perform brilliantly on the final. That's the goal, right?
Do I need to know what a factor group is?
Yes, of course you need to know what factor group is. Do you know what is factor group?